Yeah, good morning and welcome to the lecture of analog instruments. So, uh, basically, we are moving into the instruments. Till now, we have until now we have learned about the various static characteristics. Some are desirable and some are undesirable. So we got an idea about those characteristics, and today we'll start with analog instruments. And before going with that, how do we how do we classify those analog instruments? They are mainly indicating instruments, recording instruments, and integrating instruments. Indicating instruments can be of two types, that is, they can be electromechanical types and they can be electronic instruments as well. So these are the two types of indicating instruments. Okay, and then we have the next one, that is recording instruments. Recording instruments, they record the values, okay, of a period, maybe during a day. So these type of instruments are mainly used, for example, in substations. For example, in a substation, the voltmeter may record the various fluctuations of supply voltage during a day. So such instruments are widely used in areas of purpose. Then we have the integrating instruments. We know what is integration. Integration is nothing but the repeated addition. So they actually that is actually used mainly in energy meters. Energy meters are basically integrating instruments. So we will be moving to the first type, that is the electromechanical indicating instruments. So mainly in electromechanical indicating instruments, we have learned about three types of forces or three types of torques. Force or torque, both are correct, but mainly now we will use the word force, but later stage we'll be using the word torque. Okay, so these are the three different forces. One is deflecting torque, the other is controlling torque, and the last is damping torque. Very important three forces required in an electromechanical type indicating instrument. Okay, first we'll see the deflecting force. Towards the end of the last class, I have told one thing, one principle, that is, any current carrying conductor placed in a magnetic field will experience a force, and that force will actually deflect. So that can be one deflecting force, one principle behind a deflecting torque. There are various principles. It can be an inductive effect. Suppose if we have a non-magnetic conducting disc rotating between two two coils, two current carrying coils. Of course, it will experience. Of course, there will be some induced currents in that disk, and that induced current will have its own magnetic field due to the magnetic field generated inside the disk as well as the magnetic field over the disk. What happens? The disk will experience a force, and it will rotate to obey the Lenz's law. So that is what is inductive force. There can be electrostatic force also. What is electrostatic force? Two charged plates. If we bring two charged plates, irrespective of the charges, the disks will experience a force. It can be force of repulsion or attraction. There can be thermal effect also. What is thermal effect? When current is when current is flowing through a conductor, I square R losses will be there. What is I square R loss? I square R loss is basically heat. So heat is liberated. So that heat is picked up by a thermocouple, and that thermocouple converts that temperature or the heat energy to corresponding EMF. So such a principle is also used, thermal effect. And last, some indicating instruments use Hall effect. I know you know what is Hall effect. That is, if current is carried by a conductor, and in transverse direction we have a uniform magnetic field, then an EMF will be generated across the other two ends. So that is what is called Hall effect. Hall effect has its own Hall coefficient. So any effects, that is, current carrying conductor placed in the magnetic field experience a force, inductive effect, electrostatic effect, thermal effect, or Hall effect can actually um, bring in deflecting force. Okay, and that is, we learn about deflecting force when we come to the actual instruments. Okay, depending upon the instruments, these deflecting force principles may change. And then we have the controlling force. See, what is the necessary of controlling force? What is controlling force? See, some force will deflect. So when current is flowing through a conductor, it deflects the pointer. So if there is no one to control, what happens? This pointer may stop somewhere, or it may not be stopping at a point, desirable point. So which is the desirable point? So the desirable point, the pointer should stop at the desirable point, and I'll recoin the desirable point word, that is, it should stop at a final steady state point. So who decides the final steady state point? The controlling force decides the final steady state position of the needle or the pointer. So what is a final steady state point? I'll take an example. See, suppose we are having an ammeter, and we have 5 amps current flowing through that ammeter. So the ammeter naturally should read 5 amps. On the scale, the pointer should stop at exactly 5 amps point. So we are giving a 5 amps current. So that pointer should stop exactly at the point 5 amps on the scale. So how do we ensure that the pointer stops at exactly 5 amps point on the scale? See, the deflecting force will be there. The deflecting force may force the pointer to go beyond the 5 amps point on the scale. So who stops the pointer on the 5 amps point? It's a controlling force. So the controlling force is required in an indicating instrument in order that the current produces deflection of the pointer proportional to its magnitude. So when the deflection force is applied, along with the deflection force, along with the increase in deflection force, the controlling force, an opposite force, also comes into existence, and that also increases. The controlling force also increases along with the increase in deflecting force, but in the opposite direction. So the deflection force increases, along with that controlling force also increases in the opposite direction. And at the steady state point, or at the equilibrium point, or the 5 amps point, for example, then at that point the deflecting torque, the deflecting force will be equal to the controlling force or torque. So steady state point or the equilibrium point is that point where the deflecting force is equal to the controlling force. So controlling system is very important, and that is an integral part of the measuring or the indicating instrument. Without that, the controlling force, the pointer will not stop at the equilibrium point. And there is one more thing, that is, suppose we stop the experiment, the current is 0, we make the current 0. Suddenly the pointer have to come back to the 0 position. So how to ensure that? The controlling torque brings the force, brings the pointer to the back to the 0 point. And the third one is the damping force. What is the damping force? See, we know that perhaps we might have seen that is when there is a pointer, when the pointer reaches the in and around the deflection point, then there will be some swinging action like this. What is that swinging action? See, that is, it may swing to this point. This may be the equilibrium point, or maybe the equilibrium point. It may be swing between A and B. Correspondingly, after that swing, it may finally come at rest at the point O. So this swing is actually an undesirable quantity, because the swinging may take so much of our valuable time. So exactly at the equilibrium point, it should stop without any swing around the equilibrium position. So suitable damping should be there so that this swing is avoided. Okay, so somebody should be there to provide the damping force, and some systems are there inside an indicating instrument so that this damping force is provided. Okay, now we are moving to the constructional details. So of course, any instrument will have its moving system. So two requirements are there. Moving parts should be light, and frictional forces should be minimum. Why this should be light? Light means the weight of the moving part should be very small as possible, because if the weight is small, weight is very large, then what happens? The deflecting force, the controlling force, all those forces will take power from the system. See, we bring an instrument into a circuit. It should not cause any action, or it should not disturb the circuit balance, or it should not disturb the circuit functioning. Okay, so the thing is that yes, some current is flowing through the meter, but power consumption is there. The power consumption by the meter should be as small as possible. So how to ensure that? Friction should be small and the weight should be very small. or the moving parts weight should be very light. This ensures that power consumption by the indicating instrument or the instrument is very small. Okay, then the moving part should be supported somewhere. So what is the quality of that supporting system? See, we have three types of supports, that is suspension type and the taut suspension, finally the pivot and jewel bearing. The first two suspensions are mainly on the laboratory type instruments, and the pivot and jewel bearing, this is a little bit costly and they are used for what field purposes instruments. We use pivot and jewel bearings. First we'll see the suspension and taut type supports. See, suspension means that here we have, so this is a, so for a suspension type support, we don't have a spring here, we have a wire here, and 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 below we have a spring. Okay, for suspension type we have a wire here, and below we have a spring like this. So what is that wire made of? The wire is made of beryllium, copper or phosphor, bronze. Okay, so upper portion, it has a fine ribbon shaped metal filament and made of this material, and below we have a coil. A lower part of suspension is done in order to give. Okay, so uh, what is the main quality, what is the main problem with this? That is, we have only a suspension at the bottom, only at the suspension or a spring at the bottom, and this is a simple wire made of the spring material itself, beryllium copper, okay, or phosphor bronze. So thing is that we have the alignment of the instrument is very important. That is, we cannot, that is, the instrument should be correctly hung in correct vertical position. Okay, leveling of the instrument is very much important, because the position of the moving system is very important. There should be vertically positioned. The moving system should be vertically positioned. Okay, so this is actually used commonly for laboratory type cheap instruments, where we know that the instrument should be kept on a flat surface. This is to ensure that the moving system is in vertical position. Okay, and this cannot absorb shocks. Yeah, if shock is coming, then the instrument may become faulty. Okay, and then, so field type instruments never use such a suspension, and taut type suspension is a little bit improvisation to the former one. Instead of having a filament here, we have a spring itself. So this ensures that the more exact leveling is not required for such an instrument, because we have two springs at the top as well as bottom when compared to the suspension type. So exact leveling is not required for taut suspension type, because we have two springs which will absorb, or which will absorb some sort of shock, and then exact leveling is not required. But this type is also actually confined to laboratory type instruments. And the third one is the pivot and jewel bearing type, where we have a spindle. So we have a spindle which carries the moving system. So earlier two types, the filament or the spring carries the moving system. Now we have a very robust thing, that is a pivot. So the pivot carries the moving system, and the bottom of the pivot is very pointed. A conical type pointing is there, and this point is actually a semi hemisphere. Okay, semi hemisphere type, and the pivot, this end is conical, and the top and the point of contact is more or less a semi hemisphere type. Okay, and that is actually placed, or that is actually in contact with a jewel bearing. This is called a jewel bearing. Okay, so the main point is that this is very robust, and the point of contact is minimum, but the point of contact should be sufficient that it carries the stress and weight. It can bear the stress and weight. Okay, so the semi hemisphere ball at this bottom should actually carry the stress and weight of the moving system. If that is not, uh, if that is not able to carry that, then that can be breaking. Okay, the this point can break. Okay, so stress should be that should be carried by this point. Okay, so we'll see the rest of the portion in the next class. Thank you.